Okay, well, the prototypical example the prototypical example is as follows. I'll write some formula and then I'll explain what the ingredients mean. So the limit as g goes to infinity. And now I'm going to put a 1 here because with the 1 for surfaces with 1 boundary components, we will be able to understand the limit straight away. But what one should keep in mind is that the limit does not depend on which number we put here. For example, for 0, we will get the same answer.
Do you mean co-limit?
Well, yes. No. Yes. This limit is a direct limit.
Direct.
So incidentally, it's a co-limit. Okay. This thing is isomorphic to hi of omega infinity naught of something. I will explain what the something is. So we have the cohomology of or the homology of the mapping class group on in the left hand side, and the homology of something well, something strange which we don't know yet in the right hand side. Well, let's try to understand the ingredients. Well, the first ingredient is probably self-explanatory. The pi naught of the diffeomorphism group is the mapping class group, but still. Does everyone understand what the mapping class group is? Well, unless there are objections, I assume the answer is yes.
There's maybe something worth commenting on, which is that it's a kind of miracle in dimension 2 that many different groups turn out to be the same.
Yes, well, let's comment on that. So the just one remark on mapping class groups. We will consider surfaces which have marked points and boundary components. So diffeomorphisms are allowed to permute the marked points. But diffeomorphisms and isotopies are required to be the identity on each boundary component. Otherwise, there is not much difference between boundary components and marked points.
I also meant the difference between the topological and the smooth category.
Oh yes. Well, another thing, the mapping class group can be defined for every manifold, and if the manifold has a smooth structure, then there are well, at least three different mapping class groups. Namely, we can consider the topological mapping class group, the PL mapping class group, and the smooth mapping class group. And in dimension 4 or higher, these groups are not the same, not necessarily the same. In dimension 2, they're the same. In dimension 3, they're probably the same, although I'm not sure. Well, same as always. The difference between diff and PL and smooth starts in dimension 4, and it only gets worse. It only gets worse from here. Okay, so for example, for high dimensional tori, it's probably the simplest example. One can describe all three groups, and well, at least the topological and the smooth groups are not the same. Okay. Now, There's another thing which we need to mention. By the way, before we talk about moduli spaces of curves, let's take a look at this formula again. So now we understand what div plus means. Well, we sort of understand what pi naught means, but do understand what the homology of a discrete group is. In particular, Saman, Vladimir, and Mark. Do you know the definition of the homology of a group?
Homology.
Марк, Владимир, нужно ли напоминать определение гомологии группы?
Ну, сейчас это гомология классифицирующего пространства.
Да, совершенно верно. Гомология классифицирующего пространства. Владимир, имеют ли хоть малейший смысл слова гомология классифицирующего пространства?
Ну, да, I understand it.
Okay, so what about the other Vladimir? Okay, so unless there are explicit requests, I will assume that everyone is familiar with group homology.
So I would propose that we kind of assume we know what it is for today, but there were some notes that I sent Alexey, which was a course on homological stability, and it had a kind of review and also some calculations of beyond the basic sort, which are relevant to homological stability. So this might actually be a good topic for the first seminar or two. So I don't know what Alexey's opinion on this is, but we can discuss it when we discuss the schedule.
Okay, well,
it's one thing to know a definition and another thing to know how to compute something.
Well, no objections here. Okay, so indeed, if there are people who would like to give a talk on group homology and maybe with some examples, I think it's a good idea. Okay, but for now, let's assume that if G is a discrete group, okay, if G is a discrete group, then the homology is the homology of G with coefficients in M is the same as the homology of BG with coefficients in the local system, which on BG, which corresponds to M. And what is BG? Well, it's the same as EG by G. and this is the same as KG1, where EG is the classifying space for, or more precisely, EG is the universal cover of the classifying space for G and so on. Now, does what it says on the whiteboard make sense? If it doesn't, don't keep it to yourself, yell out. Okay, now let's mention modular spaces of curves, complex algebraic curves. My claim is with rational coefficients we have this isomorphism, which is not at all true for integral coefficients. Now, here, n stands for the number of marked points, not boundary components. Okay. Does okay. Well, basically, in this formula, we have the right-hand side, which we already know, and there's the left-hand side, which we will not talk about in detail today anyway. Let's try to understand why the formula is true. Let me mention one construction of the modular space. From this construction, it's not at all clear that the space is related to complex algebraic curves. But let's mention it nonetheless. What is TGM? It's a Teichmüller space. Now, what is? Does anyone know a quick way to define the Teichmüller space?
First of all, what do you mean by define? And second, what is a good way? I mean, I know that we can define it as some kind of space of metrics on a curve. But
so let's say that this is the space of metrics complete matrix. On SGN minus the marked points, of curvature -1, and let's quotient out by the diffeomorphisms which are isotopic to the identity. Now we get something. What is this something?
So is it still the case that after you delete the mark points, if I fix the complex structure, there's a unique hyperbolic metric of that curvature?
Yes, but if you throw away the marked points, it will be non-compact but still complete and of finite volume. And
and that but there's a unique metric with these properties compatible with a complex structure, or
yes.
Okay.
And basically, if you look at the proof for 0 marked points, then the idea is the same.
Mm-hmm.
Okay, so we have this definition, and it's not at all clear that the result is related in any way to the complex structure, but as Chris says, it is, and there's a way to pass from the complex structure to a hyperbolic metric and vice versa. We'll maybe talk about it later, but probably it's not worth to go into more detail today. Okay, so the action of the mapping class group on TGN is not free. So we cannot say that TGN is the universal bundle for the mapping class group, but all stabilizers are finite. So in particular, we have a map
And is it true that if we take a stack quotient, we obtain the fine moduli space?
if we take the stack quotient, we get the moduli stack, which has the right cohomology, the right integral cohomology, meaning the integral cohomology is the same as the cohomology of the mapping class group. And for rational coefficients, there is no difference.
Yeah, no, my question was that is this quotient stack the classifying stack of moduli of complex curves of the prescribed genus and number of marked points, if like consider maps in the stack sense into this object?
Well, there's well, at least topologically, yes, but the trouble is the tight Miller space is not algebraic in any meaningful sense. Chris, what do you think?
What do I think? Sorry, I missed. So I understand that the stabilizer should be finite, but what's the question?
Grisha, what's your question?
So the question was, is it true that if we take the quotient, like a quotient step, so like an infinity sheaf, then it classifies the moduli not up to like isomorphism, but it's an honest classification. So maps uniquely correspond to structures of curves, something like that.
You mean if you define something like a topological stack?
Yeah, like infinity
Then,
sheaf on some site of.
So you could define this kind of quotient either in some kind of topological stacks or try then, and then you could ask, well, if I have some nice, say, topological manifold mapping to it, what does it classify? And I think indeed it probably just classifies continuous families of these structures.
I see.
So,
Насколько я помню, все-таки это работает даже как гладкий стек, но, понятное дело, без всякой комплекс структуры, потому что, ну, как бы, нам просто с технюрой еще непонятно, какую комплекс структуру вообще брать.
Технюра вполне каноническая комплексная структура.
Их там, по крайней мере, 3.
Сейчас, ладно, хорошо, Денис, давайте, значит, мы сейчас это никогда не закончим. Okay, so so we have a map from the classifying space to MGN, and the fibers are well, they're not contractible, but they are classifying spaces of finite groups with the stabilizers, and this does not prove indicates that the map induces an isomorphism of the rational homology or cohomology groups. Okay, so we have seen two possible ways to interpret the answer in the Madsen-Weiss theorem. Well, the first option would be to take the cohomology of the group, and the second one would be to consider the cohomology of a seemingly unrelated space, namely the moduli space of complex curves. And there's also an interpretation in terms of hyperbolic metrics if people prefer hyperbolic metrics. Okay, now let's look at the left-hand side. Well, in the left-hand side we have omega infinity. Now omega infinity, as probably as people probably have guessed already, is the omega replacement of subspectrum. And well, let's see. Do we know what a spectrum is?
what is what?
a spectrum. Let's look at this definition. A spectrum is recall that a spectrum is a sequence of pointed spaces with maps from the suspension of each to the next space. Is everyone familiar with this thing? Unless there are protests, I will assume the answer is yes. Now, what is an omega spectrum? Well, an omega spectrum is a spectrum. Now, by a junction, we can pass from suspensions to loop spaces. And as a result, we get a map from the nth space to the loop space of the next one. If all those maps happen to be equivalences, then we say that the spectrum is an omega spectrum. Example. The Eilenbach-MacLane spectrum. Basically, it follows from the definition of the Eilenbach-MacLane space that we have a preferred equivalence between k pi n and the loops on k pi n plus 1, where pi is a fixed group.
So I myself don't like these kinds of questions, but if one kind of describes spectra in this way, as literally a sequence of spaces with these maps, then it's reasonable to ask, what is your favorite model of Eilenberg-MacLane spaces so that these connecting maps become evident?
Yeah, also, I don't understand why n is greater than or equal to 1.
Well, because there's no k. What is k pi naught?
Just pi as a discrete.
Just pi is a discrete group. Okay. Well, basically, there's. I don't think it changes anything. But if one wishes, one can take k pi naught to be just pi, but still, if we want negative spaces, we need to